Oh, so it's time for us to talk about transformers. What is a transformer? Well, a transformer, besides a little toy, which is a robot in disguise, is also a device that changes voltages, or sometimes it oscillates voltages. So basically, we've got three types of step-up transformer. So basically, think of it, just a second, think of a transformer as a box. We stick voltage in, we get voltage out. This side we call the primary, this side we call the secondary. And so what we do is, so we get a step-up transformer, and what that does is it increases the voltage. V. So if I put 10 volts in, I might get 20 volts out. You get a step-down transformer. And what that does is it decreases the voltage. So I might stick 10 volts in, I might get 5 volts out. And of course we also get the isolating transformer. And what that does is it doesn't actually change the voltage. What it does is it isolates the voltage. And this can be useful in things like if you were playing around with an electric drill while standing in a puddle. Now how does a transformer work? Well, if you have a loop of wire and you hook this up to an AC supply, what we do is we generate a magnetic field through the wire. So if you have a changing current, you'll get a changing magnetic field. And then if we have another loop of wire over here, and we'll hook that up to a voltmeter, what we know from Faraday's law is if we have a changing magnetic field, this will generate a voltage. So basically what happens is we have changing current or changing, and the current is going to be related to the voltage through Ohm's law. So the bigger the voltage, the bigger the current, the bigger that creates a magnetic field. The magnetic field, then changing magnetic field in this loop then generates a voltage. In reality what we do is we often will stick a chunk of steel or ferrite or something between those two loops, and this will effectively conducts the magnetic field between the two loops. So if you have a steel core, it actually makes your transformer a lot more efficient than just an air gap. So what is the voltage that's being generated? Well, we know from, other people have actually done the experiments, we know that the voltage in the primary is going to be related to the voltage of the secondary, but how are they related? So if we actually divide by the voltage by the number of turns in the primary, divide that by the number of turns in the secondary, so V is voltage, N is number of turns, of loops or turns, so number of coils that you put in there, that actually gives a strong relationship between, that basically gives the ideal case for a transformer. So let's take an example. We have an example exercise 5.5, a transformer has 100 turns on the NP equals 100, and NS equals number of turns on the secondary equals 200, and the voltage supplied, V primary, equals 5 volts. So what we do, so we know in primary, we know that, we know that's and, we know that, so we can work out that. So we go Vp over Np equals Vs over Ns. We rearrange that. I want to find out how many volts are on the secondary, so I multiply both sides by Ns. So volts secondary on the output side is equal to volts primary times number of turns on the secondary over number of turns on the primary. So this number of turns says how much magnetic field you generate. Number 2 basically says the voltage that you get out. So that's equal to 5 volts times 200 turns. Remember, turns is a dimensionless, we don't give it a unit, over 100, which is equal to 10 volts. So that's pretty cool. And, you know, transformers like this turn up all over the place. I mean, classic one is in power transmission lines. If you go to Carapero or a dam, they've got a power generator and that will put out 11,000 volts. Then they stick it through a transformer, and the symbol for a transformer is like that. So, and that goes through the transmission line at 110,000 volts or 220,000, and then it gets to Hamilton, goes through another transformer, drops back to 11,000 volts, and then it goes down to your street where your house is, and there's usually another transformer at the end of your street, and that converts it into 230 volts. Isn't that cool? But traditional places for transformers are on TV system, power systems, stage amplifiers. Yeah, it's a traditional way of changing the voltage that you're on. Because you think about it, you plug your cell phone into the wall, your cell phone might take 9 volts. The power coming out the socket is 230. How do you do that? Traditionally, you'd use a transformer. We use different technology nowadays for cell phones, but for a lot of things, we still use a transformer. Okay. So, next question is, what's our power like? Because, remember, the transformer changes the voltage, but this is the power, the voltage, the power, the energy, conservation of energy says that for a perfect transformer, the amount of energy that we stick in, we should get the same amount of energy out, which basically says power in is going to equal power out. So for a transformer, for an ideal transformer, P in, P primary equals P secondary. And remember, P equals VI. So P, power primary, is going to equal the voltage primary times the current primary, which is going to equal the voltage secondary times the current secondary. Isn't that cool? And okay, in reality, no system is absolutely 100% perfect, so transformers actually do generate quite a bit of heat. But most transformers are 90-something%, 95, 98% efficient, something like that. So anyway, let's get back to what we're doing. Let's take this example. We had an example 5. We put in example 5.5 continued. So if I have V primary, we said the V primary is 5 volts. V secondary, we got 10 volts out. Let's say the transformer is supplied with 2 amps. Let's call it 3 amps. What is the output current? So basically we know that the I primary is equal to 3 amps. So we take our equation, V primary I primary equals P secondary, I secondary. We want to find out I secondary. I secondary is going to equal VPIP over divide that by that, which is equal to voltage primary. It's going to be 5 volts, that's the input side, times 3 amps. We set the output was 10 volts, equals 1.5 amps. So basically as the voltage goes up, the current goes down, which seems cool. As the current goes up, so basically, yeah, if you drop the voltage, the current goes up. And Nikola Tesla back in the day, he was doing a whole lot of experiments. One day he made himself this transformer and it had, about 20 windings there, and it had lots and lots, and he was putting out 6 million volts. But as you can imagine, if the voltage is greatly increased, the current is greatly reduced. So he would be maybe making 6 million volts, but at a couple of milliamps. So, transformers are still quite an essential piece of equipment. We still use them all over the place. If the transformer at the substation blows, or somebody crashes into a transformer by the side of the road, you'll know all about it because you'll lose all your power. So they're still quite vital.